So today's lesson is average value of a function, and in the AP exam, there's usually quite a lot of questions that ask you about average value or applications of average value, this concept. So it seems to be more important than maybe your textbook seems to indicate that it is, because there's not a whole lot in your textbook on this. But when we talk about average value of a function, of course, the value of a function would be, we're talking about the y value of the function. So the value of a function, we're talking about the y values, okay? We're not talking about x values, we're not talking about integral, we're not talking about slope tangent lines. We're talking about literally the y values. But we are going to use integrals to find an average value of a function. But I'm just going to show you with some examples here, just going to show you what we're talking about when we talk about average value. Now I have a few graphs here set up for you. The blue one is y equals 2x. So it's a straight line. It has a slope of 2, and obviously intercept of 0, 0 here, and another point 1, 2. I have another graph, y equals 2x cubed, and that's this red graph right here. And if I zoom out, you can see how it's the cubic graph, right? We're just going to focus. Between 0 and 1, okay, for our study today, between 0 and 1. And the reason why we're going to do that is because I'm going to show you sort of how average value of a function can be sort of deceiving, but I'm going to show you what we're going to be finding before I throw out the formula there, and before we actually find average value. I want you to visualize it, okay? Now, this line right here, I know this looks really funny, okay? But what I wanted to do is I wanted to try and model a vertical line, and it's actually kind of tough to have an infinite slope, right? And these are all functions it wants me to graph. So I just chose a really, really high value for a slope. So this is not exactly vertical, but as we zoom in here, it looks completely vertical. Okay, so for our visual purposes, this is going to be acting as a vertical line. And of course, I've got a little slider here, so I can slide this somewhat vertical line all the way across. Okay. Now, why am I doing this? Okay. If you look here, this blue graph, right? The blue graph, it increases, the y value increases steadily at a completely steady rate, right? The rate of change, y to x, is consistent between 0 and 1. And of course, it's a straight line, so it's consistent over its entire domain. The rate of change is always what? What's the slope of this line? 2. So the rate of change, y with respect to x, is always 2. Okay, so that's the derivative, it's 2. Now, if we think about the derivatives for this graph in red, right, we're going to have a pretty small value for a derivative, pretty close to 0. Here, it's maybe 1. And then up here, it's pretty high, right? 2 or 3, maybe, whatever. So this is a changing rate, right? As we move from 0 to 1, let's say, the rate of change of y with respect to x varies. Okay, that's the first thing I want you to notice. What I'm going to do with this green line is I'm going to hit play here, and what it's going to do is it's going to basically run all the way across from 0 to 1, and I don't know if does that look to be stuttering a little bit for you? It's kind of jumping, which that's too bad. It never did that for me before. Maybe I've got too much going on here. Let me just pause. All right. I think it's my recording program that's doing it. That's too bad. Anyways, too much processing power. Okay, but what I want you to see, I'm going to maybe slow this down even. Okay, maybe that'll help. But what I want you to look at, and what I want you to see, is how the y values change on the blue line compared to the red line. So obviously this y value is increasing at a very steady rate. Down here though, it's not increasing very much at all at this point. Now it's increasing quite a bit quicker. And as we move from 0 to 1, the y values are increasing at a faster rate. And we know that that's what instantaneous rate of change represents, right? The derivative. So if we're talking about an average value for these functions, all right, the y value is dropping quite drastically here compared to the y value for the blue one. So let me just pause this. for the blue function, and let's just say between the intervals 0 to 1, okay, the average value of the function over this interval, because it's increasing at a completely steady rate the whole time, we're going to look at this and say, well, it's 0 at the beginning, it's 2 at the end, so the average value would probably be somewhere around 1. And you would be pretty good to say that, wouldn't you? The average value, because, you know, if you take this motion, you know, it's very steady. So the average would be about maybe half of what the y value still was. But for this one, I want you to see that as we go from 0 to 1 here, the y values initially do not increase very much at all. And when we approach halfway through the time, we're only here. So do you see how the y value, halfway through the time that we are spending going from 0 to 1, halfway through, we're only right about here on this y value, right about here. So I'm going to play this once again. Okay, I'm going to play this once again. And as it moves, I want you to watch. This is dropping pretty steadily. This has dropped quite drastically. And now is going to kind of steady state around these y values right here for a long time. Drop slowly, and to 0. So now, see, look at this. The y values are increasing, aren't they? Quite a bit. Still pretty low here. We're not going up very much at all. So the average value for this red function over the interval 0 to 1, is the average value going to be very similar to 1 for this one? Is it going to be greater, or is it going to be less? What do you think the average value for this function between 0 to 1 might be? Same as blue, okay? Any other guesses? What does the other half of the class think? Yep, for the red one. Okay, probably the same as blue. All right. So let me just say once again, when we're talking about average value, we're talking, like, think about this as a trip. You're thinking about this as a trip, and the derivative is the instantaneous speed. Okay, at any point. So on a trip, okay, if somehow you're driving in a car and your car instantaneously jumps from 0 miles per hour to 2 miles per hour and stays at that steady speed over the entire interval from 0 to whatever this end time is. The other car has a speed of 0 and then instantaneously jumps to something just barely above 0. And then it's still going pretty slow, and then it speeds up very rapidly towards the end of the trip, very rapidly, until it gets to its destination. What would the average speed for this one be? Would the average speed, do you think, be greater than 1/2, equal to 1/2, or less than 1/2? Now you're saying less. Okay? Do you want to change or do you want to stay? What do you think? You don't know. Okay. All right. You would maybe you'd maybe change your answer to maybe now the average speed would be a little bit less. Okay, if you think about it, and you're starting at a stoplight, and you start to go very slowly, and you are increasing your speed the whole time until you get to the next light, which is obviously green because you're speeding through it. But your average speed, do you think it would be exactly half of the speed you're going when you hit that light, or do you think it would be a little less? And the answer is going to be, yeah, it's going to be a little bit less, right? Now, the average speed here is pretty easy to tell because you're going the exact same speed the entire interval. But here, you see how we spend a lot of time at some pretty low speeds, and even this y value, okay? So this is distance over time. The y value is distance. The x is time, let's say. So the distance we're going, you know, not very far. I am right now, boom, at half the time that I am allowed, and I'm barely even right about here, you see? So now, now it's picking up speed. We're zooming now towards 2, zooming. So yeah, so the average value of the function over time for this blue one, I think is going to be 1, and for this one, probably going to be a little bit less. And I would tend to agree. Okay, Now that's a lot of time developing what the average value of the function actually means, okay? And I intended to do that. Because I want you to see that over an interval, because the function, if it's not linear, it's going to literally sort of spend more time at certain y values than others, okay? Think about that. Now, how do we actually calculate this? So, average value of a function. If you want to find the average value of a function, this is what you do. And we're going to use these two functions. One was y equals 2x, that's the straight line, and y equals 2x cubed. That's the cubic function. So what you do is you put the function into an integral. And then you say, okay, well, what are my limits? I'm going to test the average value of the function from 0 to 1. That's what we were looking at in our graph. And what you do then is you, in front of it, you would make a constant, which is 1 over b minus a. And of course, this is a, the lower limit of integration, and this is b. And so in order to find the average value, so let me get rid of this as a, so let's make just this as a formula, I guess. A to b, and this right here, this 2x, is actually the function. Okay? So this is how you calculate average value right here. You throw the function into an integral, you slap a 1 over b minus a in front of it, and that will give you your average value. Now, why do we do that? Well, if you think about it, what is one thing that an integral represents? Sorry? The what? The space, okay, the area underneath the graph, right? Okay, so if you think about this blue line, okay, the integral would be the area of this triangle right here, 0 to 1, and then up to 2. Okay, so 1 times 2 is 2 times a half would be 1. So that's the area of this right here, right? 1 times 2 would be 2, and then half of that would be 1. Okay. Now the area underneath this red dot, and if we're thinking about a red dot, red line, see, let's say this is that part here, and then we have all the way over here, and we have the area underneath the red. That area is going to be less, right? Okay. So if we think about integrals, the function will kind of help us visualize area underneath the graph, and that's actually going to help us determine what our average value is, because this one we decided was probably an average value that's a little less than 1 somewhere, and so the integral reflects that idea. Okay, so let's try it with this one for the 2x, and again we're going to go from on the interval 0 to 1. Okay, so 1 over 1 minus 0, integral 0 to 1 of 2x dx. That's going to be 1 over 1 times the integral of 2x. That's going to go to a 2 and then over 2. So that's just going to be x squared evaluated from 0 to 1, which is going to be x squared. No, just write it this way. It's going to be 1 squared minus 0 squared, and of course times 1 over 1, if you want to show that, which is going to be what? 1. Alright, so the average value here is given to be 1. Now if we look back to our graph, we said that 1 would probably be a pretty good average. Between 0 and 2, if we have a straight line, the average value over that interval would be 1, and it is, the y value of 1. So let's see what happens when we do this over here. So 1 over 1, integral from 0 to 1 of 2x cubed dx. So that equals, well, maybe we won't, I'll show the one there, I guess. So when we do the integral here, that goes up to 4, and then it's divided by 4, so it's 1/2 x to the 4th. 1/2 x to the 4th, and that's evaluated between 0 and 1. So it's going to be 1/2 1/4 minus 1/2 0 to the 4th, which is 1 what? 1/2. Okay, 0 to 1. So we've got 1/2 and we've got 1. So let's just see here. Let's go back to our graphs. A y value of 1 appears to be a good average value function for this. And y value of 1/2, look at this. Here's y value of 1/2, right there. And if we think about the amount of time that this function spends, down here in this range here, right, compared to how it zooms up through this one, right? See, it goes pretty quick through here, but it spends a lot of time, it goes pretty slow in here. So a y value of 1/2, that appears to be a pretty good average for that. Okay? Does that make sense? All right? So whatever the function is, you're going to be able to find an average value for that if you use this formula right here. Okay? So that's the basic introduction to average value of a function. Here's how you find it. And the actual shape of the function is going to determine sort of what that value is. Now, there are going to be some values, average values of a function, that are going to be, well, I'll tell you what, why don't you do this one? What's the average value of the sine function between 0 and 2 pi? So y equals sine of x from 0 to 2 pi. If we look at this and just think through this, what might the average value of the function be? Starts off at 0, it goes up to 1, comes back down to 0, it goes down to -1, it comes back up to 0. What might the average value be? And I didn't really write this maybe super accurate. Right? What might the average value of this function be, you think? Maybe 0. Okay, it looks like, yeah, because it goes up and then it goes down, very even rate. It goes down and it comes back up. So if we're talking about y values, it looks like, hey, maybe the average here would be 0. Okay, so go ahead, use this formula that we just learned about, and see if you can figure out what the average value of this function is between 0 and 2 pi. Okay, how'd you do with that? Did it come out to 0 for you? Sort of? Okay, did I do this right? Did this look like yours? Okay. Well, it's not cos 2x, it's just sine of x. You mean this 2 pi? Okay, cos. So what's your question? This? Yeah. Well, cos of 2 pi, yeah, would be +1. And so negative times +1. And then cos of 0 is +1 as well, so we're subtracting a -1. So that's -1 plus 1 would be 0 multiplied by your constant. Okay? Okay, so question number 2 here then is, what is the average value of the function of y equals sine x from 0 now to pi? So just in this section of the graph here. Go ahead and give that a try. Okay, so what'd you get? We have to change this to 1 over pi, I guess, right? Pi minus 0. So did you get 2 over pi? Went down? Okay. So what's 2 over pi? Well, pi is 3.14, so this is roughly 2/3, right? And if we look at the graph, and this is 1, then 2/3 would be about here, so you have an average value of about there, right? That's the value. That would be average, which would make, I think, a lot of sense. Whoops, my lines are horrible here. Would make a lot of sense because, if you have this function, it's not a straight line like this, right? It's not a straight line like that. So, then you'd have an average value would be right about there. But it's not like that at all. it's more like this, right? Where it climbs and then it starts to slow down, and then it tops out, and then it starts to gradually kind of come down again, and then falls pretty rapidly. If you're thinking about rate of change, right? So it gets up high pretty quick, and then it slows right down. So if we're talking about an average, like where are you on average? You know, where's that y value? It's going to be above a half, right? It's going to be somewhere around here. Maybe that's a bit high, but I'm exaggerating. But you know what I mean? So it zooms up there pretty quick, and then it flattens out. So think about rate of change when you're talking about average value. I would. It's pretty high, steep, and then there's a lot of these that slow right down. Okay, so the average is going to be up above what you would think would be the center. Okay, any questions? Okay, so here's your final question here for you to work on for this lesson here. Find the average value of this function y equals x minus 2 all squared plus 5 over the interval 0 to 3, and sketch the graph as well. Okay, just take a few minutes to do that. Yeah, this is what I got. So I did do the expansion first, just because integrating individual terms is a bit easier than doing your substitution maybe sometimes. But anyway, so this is what I got for the function with the integral, and 1 over b minus a here is a 1/3. So I got a value of 6, and on the graph it's a parabola that looks like this, right? And so I just kind of outlined where the y value is at the beginning of the interval, at x equals 0, and then where the y value is at the end of the integral, x equals 3. And then you kind of look at this, you know, this cycle here, and how it drops here and goes down and then comes back up. And does the average value of 6 seem to make sense? You know, and to me it does. It goes all the way down to the bottom and then just kind of comes back up again. So it would make sense that the average value would be, you know, right on here. And of course it does spend a little bit more time in this lower, these values just under 6, right? So it drops down here pretty heavily, and then kind of slows down here, if you want to think of it that way, and goes back up, right? So over this interval, here's your value of y equals 6, and that seems to make sense. If you think about the integral part of it, you know, the area underneath the graph, if you think about all this, you know, and then take 1/3 of it, okay, 1/3 of it, so that's going to be, you know, 3 times 2 is 6. Is that about 1/3 of it? Yeah, so if you think about the areas, you know, that's kind of how it works out. But I don't like to think about the area because this doesn't really help you. You know, here's the area, and then you have to figure out what b minus a is, and that's the fraction of the area of, I don't know, I don't really like it, but that's sort of how it kind of works out. And this area of 6, right here, 6, is the y value that actually is the average for the function. So it's related there. Okay, so good job. That's your that's the full lesson on just the average value and finding average value. Just give it a function over an interval, and there will be applications of finding average value of a function as we go through questions in the